My name is Mariano Zeron, and in this video, we're going to talk about the stability of the barycentric interpolation formula. So what do we have regarding the barycentric interpolation formula? So given a function f, once we evaluate it on Chebyshev points, we obtain a set v of those values. And with this information alone, we can come up with the following expression for the Chebyshev object in terms of Lagrange polynomials. By suitably modifying that expression, we obtain the barycentric interpolation formula, which has this complexity, n, when it comes to evaluating it. So it's really, really fast. But in this video, I want to focus on the stability of the barycentric interpolation formula, which is another of its strengths. Now, stability in general is an issue that is often put to one side, and we don't pay enough attention to it. So one thing is what you should get in theory when you implement an algorithm, and a different thing is what you obtain once you put it into a computer. The thing is that computers, as we know, they're not able to represent every single real value. So often they make rounding off errors, which can accumulate to the point that it gives you a completely different answer to the one that you should obtain. So what happens is that the barycentric interpolation formula is extremely stable numerically speaking. If you want to check precise results of exactly what that means, I suggest that you take a look at Trefethen's book. One of the chapters, I think, is chapter 5. At the end of it, they mention some of its properties when it comes to numerical stability. Essentially, what it means, it doesn't really matter how big this n is, that is, how many points you've used in order to build the Chebyshev object, and how many times you evaluate it, you will always get the result that you want to get without any problem whatsoever. So the first thing that we're going to show is how important Chebyshev points are in terms of stability when you use the barycentric interpolation formula. So I'm going to show you an example where we take distribution of points according to Chebyshev, and then we're going to take equidistant points, and both will be evaluated with the barycentric interpolation formula. So let's take a look at the code and see what we get. So as you can see here, the function that we're going to use is the exponential function. Now, the reason why I'm using the exponential function is it's such a well-behaved function that you can approximate it even with polynomial interpolants defined on an equidistant grid. This, by the way, is unique. It doesn't happen, of course, with all functions. And that's one of the strong points about having Chebyshev points, that it will approximate any function which is analytic in an exponential manner. Equidistant points don't do it. But for the exponential function in particular, it should happen in theory. And what we do, I'm going to run the code so that you see it. So what we do is we will be increasing the number of points on the mesh that we build the interpolant, whether it's equidistant or according to Chebyshev. And as we increase the number of points, we measure the error that we obtain. So as we would expect, in both cases, at least theoretically, you should get as the number of points increases, the error decreases. Take a look at the right-hand side of the screen. So here we've got the image of the exponential function, which is what you would expect. And here, the other graph, we've got the error decay. On the x-axis, we've got the number of points that you use to build the mesh. And on the y-axis, you've got the error in log scale. The dark blue dots correspond to the Chebyshev points using the barycentric interpolation formula, and the light blue ones correspond to the equidistant points using barycentric interpolation formula. So with the Chebyshev points, you get decreasing error. Once it reaches machine precision, it stays there. It's completely stable. But what happens with equidistant points is that at the beginning, you start seeing a decrease in the error as you would expect. And in theory, what should happen is that once you reach machine precision, you should stay there. However, the problem with equidistant points, even when you use a formula like the barycentric interpolation formula, is that as you get to around 20 points, you start getting an accumulation of errors to the point that eventually the error just becomes humongous. And that is something that, of course, you don't want to have. This is a perfect example of numerical instability. And now, as a second example that I want to show you, we're going to have the same object, which is the Chebyshev interpolant. So this is Chev interpolant, but evaluated in two different ways. One of them is going to be with the barycentric interpolation formula, and the other one is using a method called the van der Mode method to evaluate polynomial interpolants, which, by the way, is a very common method. You find it in all sorts of implementations, and people rarely know that it's unstable. So I'm going to show you now an example of that case. So now I'm going to use a different function to illustrate this case. So the cursor is being a bit slow. So it's going to be a cosine function with a lot of oscillations. And now I want to run the van der Mode method, and I want to show you the corresponding results, just as we had it in the previous example. So what do we get? First of all, we see the oscillations of the cosine function, and second, dark blue is Chebyshev interpolant or Chebyshev objects evaluated with the barycentric formula. So as you see, it takes a while for it to resolve the function. It takes about 50 points, Chebyshev points, but once it starts resolving the function, you see the exponential convergence that we would expect. And it goes all the way down to machine precision, and it would stay there. However, with van der Mode evaluation, even though it's evaluating the same object, and in theory you should have the same level of approximation, you get that the error is always oscillating around 10 or 100. So given that the scale here is of 1, we've got a humongous error in the approximation. And this is, by the way, using a very common technique to evaluate these polynomials. So the important thing to take from this video is, of course, that one thing is the object that you want to use in order to approximate. In our case, we know that has to be the Chebyshev object. Fantastic in theory, but when you implement it into a computer, you should be able to evaluate it in a way which is numerically stable. And for that, we should use the barycentric interpolation formula, which, by the way, if you move, as we showed it in the first example, if the anchor points are not exactly Chebyshev, you can have issues. But as long as you stick to Chebyshev points and you evaluate the Chebyshev object, you're not going to have any problem. And you have both the combination of how fast it is to evaluate and also the stability. So perfect match in that sense. That's all for this video. Thank you very much for following us. Please get in contact with us if you've got any queries, and see you next time.